Hello class, in this video we're going to try to solve the exercises of chapter 3. As we remember, we stopped at exercise 7 and test your knowledge. Please bring your books and open up at page 51. If your books are not with you, pause the video and open at page 51. Ready? Okay, let's start. So, a quantity of electricity of 360 coulombs crosses the cross-section of a conductor in 10 minutes. What is the current in this conductor? So, we have the quantity of charge Q equals to, let me fix this a bit. So, Q equals to 360 coulomb and time T equals to 10 minutes because we have everything we need everything in the SI unit. 10 minutes is equal to 10 times 60 seconds, that is 600 seconds. And we know that the current I equals to the quantity of charge divided by time, that is 600 divided by I'm sorry, not 600, 1 second, that is 360 coulombs divided by 600 seconds. 360 divided by 600, that is 0.6. And what's the unit of the current? It is ampere. Okay, so we have a 0.6 ampere current. Now move to number 8. So number 8 says that when functioning normally, a current of 25 milliampere, so I equals 25 milliampere, traverses an electric bulb. Express this current in ampere and in microampere. So we know that 1 ampere equals 10 to the power 3 milliampere equals to 10 to the power 6 microampere. Okay? Now, we have the current in milliampere, so to get it in amperes, we have to divide by 1,000, or we have to multiply by 10 to the power minus 3. So that's equal to 25 times 10 to the power minus 3 ampere, and that's equal to 0.025 ampere. Similarly, we want it from milliampere to microampere, so we multiply by 10 to the power 3. So 25 times 10 to the power 3 microamperes. That is 25 or 2,500 or 2,500 microampere. Okay, now we move to number 9. We will complete the following sentences. The speed of free electrons in a conductor traversed by a current is a few. So now number 9, we'll complete the following sentences. We start with A. The speed of free electrons in a conductor traversed by a current is a few. It's a few millimeters per second, so they're not really fast by themselves. But what happens is that it's not really the electron that moves all the way through the conductor, but each electron touches the other electron and so on. So the speed of the individual electron is just a few millimeters per second. Okay, so as I showed you in class, the analogy of how the electrons move, it's not really that the specific or the individual electron will move all the way through the conductor, through the wire, from the start to the end, carrying this electricity. What happens actually is that each electron moves a bit and it gives this energy to the other electron, and so on till it reaches the end of the conductor. Okay, now part B. The speed of establishment of electric current is equal to, well, it's really high, it's almost equal to the speed, so it's really high, it's in the order of 300,000 kilometers per second. 300,000 kilometers per second. So if you imagine what's happening here, so the speed of individual electrons is a few millimeters per second, but all together when they touch each other, how the electricity, how the current will move from the beginning or from the start of this conductor to the end, it's really fast. Okay, it is almost 300,000 kilometers per second. Now C, what is the device used so what is the device used to measure really low currents? So the apparatus which serves to measure very low currents is called, so we go to page 47. On page 47, there are listed there some instruments to measure a current. We have the analog ammeter, we have a connection, this is the connection of the analog ammeter. They show you how it's connected, and then you have the multimeter used in ammeter, and then finally we have something called the galvanometer. A galvanometer is a very sensitive ammeter. Okay, so to measure this really low current, we use what is called the galvanometer. Okay, well, there are actually other types of devices that can be used to measure really low currents, such as the pico ammeter, and pico is a suffix that stands for the power 10 to the power minus 12. Okay, just as the micro is 10 to the power minus 6, pico is 10 to the power minus 12. So it's really small. Now let's continue with our questions. Let's move to number 10. So, true or false? And we have to correct the false statements. Part A. To measure a current of 0.4 ampere, we can use the scale of 200 milliamperes. Okay, so let's start by saying 200 milliampere equals to 200 times 10 to the power minus 3 amperes, right? That is 0.2 amperes. A scale which is 0.2 amperes, it measures the maximum value that it can measure is 0.2. So can it actually measure a 0.4 ampere current? No, because 0.4 is greater than 0.2. So part A is false. And we say that a 0.4 ampere current can be measured by a 400 milliampere scale or a 500 milliampere scale, but not a 200 milliampere scale. Let's move to another page now. Now, part B. In an electrolyte, the current is due to the flow of electrons. Well, if you remember the electrolyte, it, like the galvanic cell it's called, right? what flows is not electrons exactly. What flows are the negative ions inside the solution. So false, and instead of electrons we say the negative ions. Let's continue with C. To measure the current in a series circuit, we can connect the ammeter at any point of the circuit. So let's see here. This is a battery. These are a few lamps connected in series. Wherever that we measure the current, so if we put the ammeter here, or we put it here, or here, it's the same current passing through. So number C is true. Let's continue now with the questions. So now, second part, which is the questions. The first question is number 1. You are asked to measure a current with an ammeter with many scales. In what order do we use these scales? So we don't know what is the current or the value of the current that we are measuring. So naturally, we're going to use the highest scale that is provided by this ammeter. And then when we know the value of this current, we adjust the scale based on the current that we have. So we choose a value that is close to this current but still higher than this current. So we will answer by saying that we use the highest scale first. Now, for example, if we measure a current, let's say we have these scales, 1 ampere, 500 milliamperes, and 100 milliamperes, let's say. Let's say these are the scales that we have. And when we first want to measure the current, we choose 1 ampere. When we choose 1 ampere, the current appears to show that it is 0.3 amperes. 0.3 amperes, that's equivalent to 300 milliamperes. So the convenient scale would be this one. So after we first choose the highest scale, which is 1 ampere, we adjust it to 500 milliampere to give us a more accurate value. Okay? Now, let's move to, look ladies, I am gonna give you a PDF. I'm gonna send you a PDF file of these answers. So just focus with the answers now and you're gonna copy them later, okay? On your notebooks. Number 2. Does the current in a resistor depend on the speed of the electrons? So actually, the current that passes through a resistor does depend on the speed of the electrons, because as the speed of the electrons increases, the number of electrons that cross a unit area of this resistor per each second increases as well, so the current will increase. So the current in a resistor depends on the number of electrons, on the speed, of the electrons, because as the speed increases, the number of electrons that are going to pass per unit of time will also increase, and thus the value of the current will actually increase as well. So we will answer by saying yes, because as the speed of the electrons increases, the number of electrons passing through the cross section of a resistor or of the resistor increase as well. Now, as the number of electrons passing increases, the value of I will increase as well. Okay? Now, let's move to number 4. So, number 4, it says that in a circuit of figure 3.27, let's draw the circuit of 3.27. So, number 4, we have a battery. We have these loads here. Let me draw the loads in white. And we have a switch as well. Okay. A load here, a load here, and we're gonna connect we have another battery here on the other side. Sorry. Okay. We call here K1 and K2. We have here I1 and I2. K1 and K2 are the two switches. We have I1 and I2 and I here passing through this load here. So the first question is, what is the relation between I2, I3 and I1, I2 and I3? I guess I3 is just I. Okay, well, we know that at this junction here, the currents, their currents are added because they're based on the law of Kirchhoff currents law. So I1 plus I2 equals to I or I3. Okay, that is number A. Now B, how is the relationship changed if K2 is opened? So if K2 was opened, let's open K2. K2 was opened, then there is no current actually passing here. There's no I2. What happens is that I1 will continue its way into this branch and it would be the same. So what happens would be that I1 would be equal to I3. Now, can you deduce, that is part C, part B, I'm sorry, where's this? This is part B. Now part C, can you deduce that the uniqueness law is particular case of the junction rule? So the uniqueness law is actually a particular case of the junction rule in case there is no other current passing. Like if the junction was just of two branches, let me draw it here. So we know that the junction rule says that the sum of currents in many branches is equal to that, like the sum of currents in are equal to the currents out. So 1, 2, 3, 4, 5, 6. We know that I1 plus I2 plus I3 equals to I4 plus I5 plus I6, etc. This is the junction rule. This question says that can we deduce the uniqueness law of the current, saying that it's a particular case of the junction rule? Exactly, it is. So if we want to say that this junction here consists of one current in, one current out, 1 and 3, as here, I1 would simply be equal to I3. Okay? Now, what I want you to do for next time is that I want you to solve exercises or problems 1, 2, and 3. In the next video, we're going to solve these problems 1, 2, and 3, and if we have extra time, we're going to solve 4, 5, and 6.